Hello and welcome to G Fun Facts Online, the show that dives deep into the science that's shaping our future. Today, we're talking about your phone, your laptop, your entire digital life. All of it runs on a simple principle, controlling the flow of tiny charged particles called electrons. For decades, we've treated the electron like a one-trick pony, valuable only for its negative charge. But what if I told you the electron has a secret, a hidden property that we're only just beginning to unlock? A property that could spark a technological revolution bigger than silicon. This is the story of electron spin and the dawn of a new era called Spintronics. Stick around. You've probably never thought about an electron as anything more than a tiny point of negative energy. But in the weird world of quantum mechanics, an electron also behaves like a microscopic spinning top. It's constantly spinning, and this spin creates a tiny magnetic field. This spin can be oriented in one of two directions, which physicists call spin up and spin down. Now, think about the language of computers. It's all based on zeros and ones. In traditional electronics, we create those zeros and ones by pushing or holding back a bunch of electrons. But in Spintronics, we can use the spin-up and spin-down states as our new zeros and ones. Why is this a big deal? Well, the advantages are staggering. First, speed. Flipping an electron's spin from up to down is much faster and takes way less energy than physically moving a whole crowd of electrons around a circuit. This means faster processors and more responsive devices. Second, power consumption. Because it takes less energy, spintronic devices would be incredibly efficient. Imagine a smartphone that lasts for days, not hours, or massive data centers that use a fraction of the electricity they do today. Third, and this is a big one, is non-volatility. Spin-based memory holds its information even when the power is off. No more boot-up times. Your computer would be instant on, always ready, and your data would be far more stable. Finally, density. By using both charge and spin, we can pack way more information into the same amount of space, leading to storage devices with mind-boggling capacities. This whole revolutionary field didn't just appear out of nowhere. It started back in 1988 with a discovery so important it won the Nobel Prize in Physics in 2007. Two scientists, Albert Fert and Peter Grunberg, discovered something called Giant Magnetoresistance, or GMR. They found that if you create a sandwich of materials with alternating, ultra-thin layers of magnetic and non-magnetic metals, the electrical resistance of that sandwich changes dramatically depending on the spin of the electrons in the magnetic layers. If the spins in adjacent layers are aligned, electricity flows easily. If they are opposed, the resistance skyrockets. This wasn't just a cool lab experiment. This GMR effect became the key to creating the supersensitive read heads in hard disk drives. It's the reason your computer's storage capacity exploded in the late 90s and 2000s. GMR was the technology that officially launched the field of spintronics. But to take spintronics to the next level, beyond just reading data, we needed a very special material, a stage for this spin revolution to play out on. We needed a material that could let electrons and their spins travel long distances without getting scrambled. For a long time, this was a huge roadblock. Then, in 2004, came the discovery of a true wonder material, a material that seems almost perfectly designed for spintronics. Enter graphene. You've probably heard of graphene. It's a single layer of carbon atoms, just one atom thick, arranged in a perfect honeycomb pattern. It's the thinnest, strongest, most conductive material ever discovered. And for spintronics, it's a dream come true. Here's why. The single most important property for a spintronic material is what's called spin diffusion length. That's just a fancy way of asking, how far can an electron travel before its spin information gets randomized and lost? In most materials, that distance is incredibly short, but in graphene, An electron can travel for tens of micrometers with its spin perfectly intact, even at room temperature. That's a marathon in the quantum world. This happens for two key reasons. First, graphene is made of very light carbon atoms, which means an effect that usually scrambles spin, called spin-orbit coupling, is incredibly weak. Second, the most common type of carbon atom has no nuclear spin, so there's no interference from the nucleus to mess things up. Graphene is like a perfectly smooth, quiet highway for electron spins. On top of that, electrons zip through graphene with almost no resistance, a property called high electron mobility. This means signals travel fast and efficiently. And perhaps most importantly, you can tune graphene's properties on the fly. By applying a simple external electric field, you can change how many electrons are in the graphene, which gives you dynamic, real-time control over its spin transportabilities. This is the key to building spintronic logic gates, the building blocks of a new kind of computer. So, how do you actually build a device with this stuff? You need to do three basic things. First, you have to inject a current of spin-polarized electrons into the graphene. That means getting a stream of electrons that are all spinning in the same direction. Second, you need to transport that spin information across the graphene sheet. And third, you need to detect the spin state of the electrons at the other end. The main tool scientists use to test this is a device called a lateral spin valve. Imagine a tiny strip of graphene. On it, they place a series of tiny magnetic electrodes. One electrode, the injector, shoots a spin-polarized current into the graphene. These electrons then diffuse sideways along the graphene highway. Further down the road is another magnetic electrode, the detector. This detector measures the spin state of the electrons that arrive. By checking the signal at the detector, scientists can see exactly how much spin information successfully made the journey. Initially, there was a big problem. A conductivity mismatch between the metal electrodes and the graphene was like a massive traffic jam, preventing spin from getting into the graphene efficiently. But researchers found a clever fix. They placed a super thin insulating layer, just a few atoms thick, between the magnet and the graphene. This tunnel barrier acted like a perfect on-ramp, solving the traffic jam and boosting the spin signal dramatically. But just moving spin from point A to point B isn't enough. To build a true computer, you need to manipulate the spin. You need to be able to flip it from up to down on command. This is where things get really exciting. Researchers are developing incredible techniques to do this. One is called the Rashba effect. By layering graphene on top of certain other materials, you can use an electric field to create a sort of virtual magnetic field that can precisely rotate the electron spins. This is the concept behind the spin transistor, a device that could replace the silicon transistors we use today. Another technique is using magnetic proximity effects. By placing graphene right next to a magnetic material, you can actually make the graphene itself temporarily magnetic, giving you another way to control the flow of spin. These tools are the key to building spin-based logic gates, the foundation for a whole new paradigm in computing. Of course, there are still challenges to overcome before graphene spintronics is in your next smartphone. Most of this groundbreaking research is done with tiny, perfect flakes of graphene peeled off graphite, using what is affectionately known as the Scotch tape method. For commercial products, we need to be able to grow huge, high-quality sheets of graphene reliably and cheaply. We also need to make sure the devices can be manufactured with high precision every single time, and, crucially, that this new technology can be integrated with the existing silicon industry. But the potential payoff is truly transformative. We're not just talking about faster computers with longer battery life. Graphene spintronics could be a cornerstone for quantum computing, using the long-lasting spin states in graphene as the qubits that power these incredible machines. We could build neuromorphic, or brain-inspired computers, using spintronic devices to mimic the synapses and neurons in our own heads. And because graphene is flexible and transparent, we can imagine a future of wearable spintronics, smart clothes that monitor our health, or foldable paper-thin displays. The marriage of graphene and spintronics is pushing us beyond the limits of conventional electronics. By embracing the electron's hidden spin, we are fundamentally reimagining the future of information technology. The path is challenging, but the age of spin is here, and graphene is leading the charge. Thanks for tuning in to G Fun Facts Online. If you enjoyed learning about the future of technology, be sure to like, subscribe, and hit that notification bell so you never miss an episode. Until next time, stay curious.